In this part of the podcast, I'm going to take a closer look at the principles underlying the Haskell type system. First, I will present a simply typed language that does not have polymorphism at all, and we'll see how we can describe that and give a nice type system for that simply typed language. And then we're going to add parametric polymorphism and see how we do that. It's not so difficult, actually. In the next session we'll then add ad hoc polymorphism as well, and we'll talk about type inference. But for now, I'm going to present the simply typed language and then add parametric polymorphism. Before we present the simply typed language and its type system, it's a good idea to first have a look at the components of a type system. A type system for a programming language always consists of a definition of the abstract syntax of the language. And one does that in the form of formation rules. And the abstract syntax tells us what programs are going to look like. Then there's a definition of the set of types, and that also takes the form of formation rules, and they tell us what types look like. And then we must define the format of type judgments. That will tell us what type judgments look like, and this will tell us what we can talk about in the type system. And finally, we must define the set of valid type judgments, and to do that we have a collection of type rules. So these are the components of a type system, and let's look at the first one. In our simply typed language, we are dealing with expressions. We'll call the syntactic category of expressions exp, and whenever we speak of an expression we'll call it e, so e belongs to exp. We also want to have constants. Constants belong to the set of constants, and we have variables x, and they belong to the set var. E, c, and x are what we call metavariables. So variables can be called anything, not just x, but whenever we speak of a variable and we don't know what it is, we'll refer to it as x. And sometimes we will want to refer to functions, because functions also have identifiers. We'll call them f. Anyway, the formation rules in our language are quite simple. An expression can be a variable, it can be a lambda expression, it can be an application. So far this just looks like the lambda calculus, and it is a version of the lambda calculus. But we've also got pairs of expressions, and we've got constants, and we've got local definitions. Let x equal e1 in e2, and this x here could be a variable, or it could be a function identifier. And finally, biconditionals. If e0, then e1, else e2. So constants, what are they? Well, naught is a constant, successor is a constant, true and false, and is 0 are the constants here. This allows us to capture the natural numbers. and the truth values. And here we can test for 0. This does not look very impressive, but it's really all we need. We could add lists and strings and what have you. It doesn't add very much. It doesn't add anything to the expressive power of the language. And as far as the type system is concerned, it wouldn't matter very much either. So there are reasons why we stick to the simply typed language for now. Next, let's consider a version of the language of types that has no polymorphism, a set of simple types. And the set of types is defined by formation rules. We let T range over the set of types, so T is the meta variable for types, and T can then either be a base type, it can be int, or it can be bool. So these are what we call base types. Or it can be a function type, T1 arrow T2, or it can be a product type, T1 times T2. This is what you would call T1, T2 in Haskell, but usually when we speak of type lambda calculus, it's customary to use the Cartesian product symbol. So I'll stick to that here as well. The format of type judgments is quite straightforward. We say that expressions have a type T, but expressions may contain variables. So in order to find the type of an expression, we need to know the types of the variables, and to that end we have a type environment. And the type environment, what's that? E is a function, it's a partial function in fact, from the set of variables to the set of types. So now we know what type judgments look like. All we need to do now is describe what type judgments are valid, and to this end we have type rules. Now let's define the set of valid judgments, and as I said, we are going to use type rules for that. We've already seen most of these type rules, in fact all of them but one, in the first session, but it's probably a good idea to recap them. We're going to have a type rule for each of the constructs in our language. So if we look at the formation rules for our language, we can see what type rules we should have. An expression could be a variable, so we're going to have a type rule for that. The type of a variable x is T with respect to the type environment E, if it's the case that if you apply the type environment to x, if you look up x in the type environment, you get the type T. Now, how do we type a pair? Well, if we have a pair, E1, E2, and we type it in some type environment E, then the pair should have type T1 times T2, and T1 should be the type of E1, and T2 should be the type of E2. Next, we've got if then else. If we're typing an if then else, a conditional expression in some type environment E, then what we want is that the two branches of the biconditional have the same type T. Moreover, the condition E0 must have type bool. So the two premises, apart from E0 having type bool, should be that E1 has type T and E2 also has type T. So that's how you type a biconditional. How do we type a constant? In order to do this, we actually need to have an additional element in our type system, because we need to have a function sigma that, for constants, tell us their type. So we also assume a constant environment. So given that we have a constant environment sigma, then C gets the type T with respect to E, if it's the case that if we look up the type of C in the constant environment, it's T. Now, local definitions, let expressions, how do we handle those? If we have a let x be E1 in E2, that's got type T with respect to the type environment E. If it's the case that we can type E1 with type T1, and then we add the assumption that X has type T1 to our type environment, and given that added assumption, in the new type environment we can then type E2, and the type of E2, T, is then also the type of the let expression. Now you may wonder, is the let expression a recursive let expression? Can we write recursive functions using this? Could we have E appear in E1? And the answer is no. X cannot appear in E1. So let's expressions are not recursive. How can we see that we disallow this? Well, we can see this here, in fact. When we try to type E1, we notice that X is not mentioned in E. So, from the typing rule, we see that let expressions cannot be recursive. Well, they could be recursive, but then we cannot assign them a type. So we do not allow recursive let expressions in this type system. The last two rules are the rules for abstraction and application. If we have an abstraction, lambda x e, then how do we find the type of that given a type environment E? Well, the type of a lambda abstraction should be a function type, T1 to T2. And if we, to our type environment, add the assumption that the formal parameter x has type T1, then we should be able to conclude that the body, which is not E2 but just E, has type T2. Finally, for an application, if we have E1, E2, then E1 must have a function type T1 to T, and then E2 must have a type that's T1 also, because we must be able to use the function E1 with the argument E2, and the type of the expression should then be the return type of E, and that's T. So that's the rule for application. And these are all the rules of a simply typed language.